Yes, sir, we can start now.
Okay. Okay. So basically, what is happening that here, so there are in machine learning, you can say there are two schools of thoughts. Okay. So let me just write it out. I think it will be helpful for you to understand. So one is the discriminative models, and another is generative model. So machine learning per se. Okay. So it is having just 1 minute. Yeah. So can you see my screen? Can you see my screen? Please respond.
Yes, sir.
Okay. So basically, if you look at this, if you look at this machine learning, okay, thank you. So machine learning, if you look at, okay, so in machine learning, there are two schools of thoughts. Okay, one is discriminative way of looking at predictions, discriminative models. Discriminative models. I think there is a problem at this particular space. Discriminative models and generative models. Okay. So discriminative models, this is basically if you look at, so how does it work? And conventional, all these particular machine learning models, they are of discriminative models. This is basically kind of discriminating the data examples, okay, from one set to another set, and based on this another set. So what happens that for discriminative models, the best kind of model, or best kind of, you can say, um, best kind of example, I think it is the support vector machine. Okay, so suppose you are having a classification task. Okay, you are having a classification task. So here two types of points are there. Suppose this is positive class points, and here it is another is negative class point. Okay, this is suppose negative class points. Right, now you want to use discriminative models to predict whether a particular point will be a positive class or negative class. Okay, so this is a classification problem. So what you are doing, you are basically trying to identify a boundary. Okay, that is basically identifying. Let me use some other color. So we are trying to identify the best boundary. Okay, we are trying to identify the best boundary, so that below this boundary it is positive examples, and above this boundary it is the negative examples. So this is suppose x1, this is x1 variable, this is x2 variable, and this is suppose a positive class, negative class. Okay, so in discriminative models, we are trying to generate a boundary that will be discriminating the positive classes from the negative class, positive class points from the negative class. Now in support vector machine, basically what it does, it is doing one step ahead. It is actually going. So it is actually creating the maximum margin possible along with this particular discrimination. Okay, so is this the best boundary? Somebody will tell, okay, no, this is not the base boundary. The base boundary is suppose this one, or the base boundary is suppose this one. Okay, this is the base boundary. Okay, why? So base boundary, it might mean many things to many people. Okay, somebody is telling that it should be nearer to the positive class, and it should be away, maximum away from the negative class. Okay, somebody is telling no, negative classes are more important. You have to remove those negative classes from our life. So negative things you should remove, and the boundary should be, you should have maximum space towards the positive class. Okay, so that's why it should be actually nearer to the negative class. Okay, now there might be several boundaries possible. Okay, so there might be, so this can be another boundary. Okay, this can be another boundary. Now the so I can have many boundaries possible. Okay, I can have many boundaries possible. Now can I basically unify all these boundaries and tell, okay, this is the best margin. Okay, this is the best margin. Okay, for my so now we are not looking at the boundary. Boundary is one line only or one plane only. Now I'm telling that this should be the margin. Okay, that upper value of the boundary and lower value of the boundary. So support vector machine is actually doing that thing. So that's why support vector machine is known as maximum margin classifier. Okay, support vector machine. So how many of you have heard of this particular term, support vector machine? Maximum margin classifier. Okay, so this is also a linear regression kind of model, but its working is little bit different. Okay, it is actually talking about uh, maximum margin. Okay, and for classification purpose, it is mainly used for classification purpose, but you can use it for continuous response also. Okay, so this is basically discriminative model. So in discriminative model, we are trying to find out relationship. Okay, so y equals to fx plus epsilon. This kind of relationship I want to find out. So this will be acting as a boundary. So this is the equation of the line. Whereas generative models is actually talking about what is the probability of class 1 given x, or you can say class 1. Suppose I am telling that what is the um, probability of class positive class given x, and what is the probability of negative class given x. Okay, so what is the probability of negative class given x? Okay, so can I find it out? Now, whenever you are going to find it out, so this will be kind of, as this is conditional probability, so this will be x given plus multiplied by plus, okay, divided by p of x. Similarly, this will be probability of x given minus, okay, multiplied by p of minus by p of minus. Now, if you look at these generative models, then I think knife-based classifier is the, you can say, the most basic kind of generative model you can start with. But the problem is that it is actually ignoring the hierarchy of the data predictor variables. Okay, hierarchy of the predictor variables, as well as the parameters. It is actually ignoring the hierarchy. If you don't ignore the hierarchy, then it is becoming huge computation actually you have to do. Okay, huge computation you have to do. Okay, so that's why basically if you come out of this naive based classification, that's why it is called as naive. Okay, because it is not exploiting the uh, you can say the relationship between the predictors, that who is causal, who is effect, and all these things. Basically it is not looking at, it is just taking them all as it is. Okay, so it is actually too much computation you need to do when you are going for even moderate kind of data set for classification purpose. Okay, so that's why knife-based classifier it is used, but the thing is that its usage has come down. Okay, over time. Now in generative models, okay, so we are now interested in this particular conditional probabilities, class probabilities. Okay, given that we are now interested in the joint probability also. Okay, that y, x, then theta. Okay, so actually generative models are of this nature. We are exploiting this particular joint probability. Okay, we are exploiting this joint probability of all the uh, parameters as well as variables, joint probability, rather than conditional probability. So this is generative models. Okay, but uh, as we are in joint probability, so conditional probability will be coming. Naturally, it will be coming. Otherwise, how will you do that? So generative models are basically inherently probabilistic in nature, and it will be in the more of the cases, it will be all conditional kind of things will be coming into picture. Okay, conditional probability, joint probability, that will be coming into picture. Achha. So this is why my interest or my motivation for this particular thing is to create the Bayesian literacy and all this kind of conditional probability, joint probability, whatever you tell, na. So naturally Bayesian statistics will be coming into picture, because Bayesian framework is much more wide ranged as well as very you can say structured framework to look at these kind of problems. Okay, so that's why if you can understand, if you can actually consider all these kind of this machine learning models in a hierarchy form. Okay, so here what is happening, suppose if you talk about linear regression. Okay, if you call about linear regression, then in linear regression, we are assuming the equation to be y equals to x beta plus epsilon, right? And epsilon follows normal distribution with mean 0 and variance sigma square, right? Now the beta, I am assuming that it is also following a normal distribution with suppose mean. So mean is suppose mu beta and variance is sigma beta square. Okay. Now, along with this, I am telling that the sigma square, okay, the sigma square is actually following inverse gamma distribution with A naught and B naught. In this way, I'm having a hierarchy. Okay. So I'm having a hierarchy. So I can actually start with this P of, so the what are the parameters here? I want to estimate beta and sigma square. Beta and sigma square given y and x, right? Beta and sigma square given y and x. So this is the posterior I want to estimate. So this posterior can be written as P of y given x beta sigma square. Okay. Now come to the next level. So this is the likelihood. Now come to the next level, that P of beta. Suppose if I tell, okay, so beta is actually dependent upon, is it dependent upon anything? Yeah, it is dependent upon this mu beta and sigma beta square, as well as I'm telling that it is dependent upon sigma square also. Okay, so this can be the prior on the beta. Okay, then P of sigma square, like this it is going. Okay, now prior of sigma square is prior on sigma square is inverse gamma a naught b naught, b beta distribute prior on beta, it is normal distributed. So here what will happen, that it is, I am telling that it is dependent upon sigma square. So this sigma square will be entering into this sigma beta square. Okay, and it will be having joint, you can say, variance. Okay, now you can have this graphical model by which you can tell that how these different variables and parameters, they are actually getting affected by one another. Okay, so here this is called as plate model. Okay, so plate model is basically that suppose y, this is the response. So response is getting affected by this side x. Okay, and this side, another side is basically beta. Okay, and this side it is the error. So this is epsilon. Now epsilon is getting influenced by what? That is normal distributed with variance sigma square. So here it will be sigma square, and then sigma square is actually coming from inverse gamma distribution having two parameters a naught and b naught. So one side it is a naught and another side it is b naught. Okay, so this is kind of hierarchical model. Achha, beta is getting influenced by what? It is a normal distribution. Okay, so two parameters, so mu beta here and sigma beta square here. Right now, this is basically here it is the hierarchy. Right now, it is basically depend how the data we are getting. We are getting the data as this is suppose one plate. Okay, so y1 and x1, right? Y1 and x1, like this I can have several plates. Okay, I can have several plates. Okay, so n times I can actually have. right? So this is first one, this is second one. So what does this plate mean? Plate means that it is one observation in the data set. Okay, and how y is actually getting affected. So it is getting affected by three things. It is I'm calling it affected because um, mm, in regression generally what happens that we are exploiting the correlation nature. If you are talking about the frequentist approach, we are actually exploiting the correlation nature of correlation, that how y is changing for changing the value of x. Okay, it is actually exploited. But in case of Bayesian, we are actually exploiting the Bayesian inherently it is causal in nature. Okay, so we are exploring and exploiting the causality also. So because whenever you are having this kind of conditional probabilities, they are causality, they are exploring the causality, they are no more in only is correlation. Yes, from correlation it is getting motivated. But the thing is that causality actually, you can say, uncovers much more than correlation. Okay, so causality is telling about that who is the cause and who is the effect. Okay, in that way, basically it is happening. Okay, I'm not going into that causality and correlation. That is a big debate. Okay, but Bayesian inherently it is causal in nature. So let me just now look at this particular lower bound. Okay, so just lower bound, how it is getting calculated. So evidence lower bound for this linear regression. Earlier it was linear regression, right? Linear regression we did. So linear regression I am continuing. So continuing the linear regression. So evidence lower bound for linear regression. Acha, I am having one plan. I was just trying to get a feedback from you that if I start taking the quizzes after these theory classes are over, means from Friday, if I float the quizzes, and if I take 2 days, means not two weekend, I am telling. So Saturday and Sunday, if I give it to you, so can you complete 5 quizzes in those 2 days? Is it possible? So can you please respond? Then I'll be floating the quizzes. I'll be floating the quizzes on Friday. Okay, so I can extend it till suppose next Tuesday. Take 4 days time. Okay, take 4 days time and go through the lectures. Identify where are the problems. Wherever you are finding problems, just revert back to me. Okay, so if you are having any kind of problem, prepare yourselves. Then take the quizzes. So will it be okay? So if I start floating the quizzes from Friday onwards, I think that will be helping you, because you'll be getting good time at least in the weekend to focus on your studies. Okay, or you can say digesting all these lectures. Okay, and then it will be easier for you to go for attempting the quizzes. Is it okay? So I'll be floating it on Friday onwards. Okay. Acha, so okay, so evidence lower bound, it is for the Q will be finding it out. So evidence lower bound is given as uh, expectation of the joint distribution, log of joint distribution first. Okay, that is the true posterior. So in case of linear regression, it will be beta, then alpha, and then y. Okay, minus the approximated one. So ln q w and sorry beta and alpha. Okay, ln q beta and alpha, right? So if I break this, the first one, so this will be e of beta ln uh, P y given beta, okay, plus E of next one is ln P beta given alpha, right? Beta given alpha. So, and the expectation will be in terms of beta and alpha plus E of ln P alpha, okay, and the expectation is with respect to alpha, minus expectation of alpha, sorry, expectation of minus this one is, acha, for q beta and alpha, that will be ln q beta plus ln q alpha. So this will be ln q alpha, okay, minus, so minus, yes, minus, and ln q. Yeah, I'll be giving. So, suppose if I keep the deadline till next Tuesday, okay, I think we'll be getting enough time. So my aim is go through these lectures as much as possible. Okay, you might be having many questions. Why did it happen? Please come back and ask. Okay, if it is by me, then I'll be definitely answering. And if it is not by me, I'll be passing the questions to the faculty, concerned faculty, and I'll be trying to get it replied. Okay. Okay. Next is that E of ln P y beta with respect to beta will be E of beta n by 2 ln rho by 2 pi, then minus rho by 2, then y transpose y plus rho, then mn transpose mn. So I am actually, sorry, mn transpose, not mn, mn transpose, mn transpose, then x transpose y, okay, and then minus rho by 2 trace of, okay, so trace of x transpose x, then mn transpose mn. So what is this mn, by the way? That is the, you can look, here is the mu n. Okay, so mu n I had actually given. So this mu n is actually mn. So let me just change it to mu n. Mu n, mu n, mu n. Okay, and then so this one is mu n transpose, mu n transpose plus Sn. Yes. Okay. So what is trace operator, by the way? Trace, trace of a matrix, it will be summation of all the diagonal elements. So A is suppose, so A is suppose A11, A12, A21, A22. Okay, so trace of A will be A11 plus A22. So summation of the diagonal elements. So here also trace of x transpose x multiplied by mu n transpose Sn. Okay. Acha. Now this must be kind of, this will be a single value, scalar value. Okay, so that's why this, all the things are actually coming in this way. Okay. Acha, then E of alpha ln, E of alpha and beta ln P beta given alpha. Okay, so this is coming as minus m by 2 log 2 pi plus m by 2. Now something, this psi operator is coming. This is called as digamma function. Okay, psi an minus ln bn. Okay, so this is basically, you need to go by the derivation. I'm just writing the final result. Okay, so to implement that, an by 2 bn multiplied by mn transpose mn plus sn. Oh, trace of sn. Okay, so let me write it clearly. So lots of mathematical formula are there, so please bear with me. So next is E of alpha of ln of ln p alpha. Okay, so here it will be a0 ln b0 plus a0 minus 1, then psi an. Psi function is known as digamma function. You can find it in Wikipedia, digamma function. Okay, psi an minus ln of bn then minus b0 an by bn minus ln gamma a0. Okay, then expectation of the, now coming to q. Okay, so expectation is expectation of ln qw with respect to w is coming as half half ln of determinant of Sn plus m by 2 1 plus ln 2 pi. Okay, you can actually find it out. I think it is not a very difficult thing. So this will be the beta. What happened? It is not working. My this is beta. Okay. So next is eraser is not working. What happened? Another is E of alpha ln q of alpha is coming as ln gamma function of an minus an minus 1, then psi function of an minus ln bn plus an. Okay, now this, what is the use of this particular evidence lower bound for this kind of inference? Evidence lower bound must be maximized. Okay, so you can actually use it in two ways. You do coordinate ascent variational inference. For each of the update, find out this evidence lower bound, and this evidence lower bound must be increasing over iteration. Okay, and after a certain point of time, so elbow will be actually going, must go like this. This side it is elbow with iterations. Okay, so if elbow is coming down or fluctuating too much, that means you are having some kind of problem in the inference. Okay, so set the initial values again and then try to do it. Okay, or you might be having some kind of erroneous coding. That's why this is happening. Getting my point? In this way, basically elbow will be useful on one side. Okay, so usage of elbow. First is that it must be non-decreasing. Okay, it must be non-decreasing. Second, directly you can optimize this elbow. Okay, you can optimize this elbow directly, and you can find out that what will be my best value of the parameters. Okay, elbow can be optimized directly to find out best value of the parameters, to find out best parameters. Okay, so in these two way we can actually use this elbow. Okay, okay, now we are going into this logistic regression. So just 1 second, I'm getting some message. Okay, so now I am coming to logistic regression. Now logistic regression having some problem. What is the problem? That logistic regression likelihood is Bernoulli. Okay, and Bernoulli does not come in the Gaussian family. Okay, so that's why this is a big challenge, right? So we have to do something so that we can actually we have to do something so that we can actually come out of this particular difficulty. Okay, so we have to do some kind of modification. So variational inference. Arey, where the arey, where the other portion? 1 minute. Arey, I have written so much in this, but it didn't come. Arey, what happened? Okay, please bear with me. I have to write it once again. I don't know where did it go. So E of arey, Spain is also not. You have screenshot. Okay, just 1 minute. What happened? This is this is slideshow. Okay, E of alpha, ln P of alpha. Okay, that is coming as a0 ln b0 plus a0 minus 1 psi an minus ln of bn, okay, minus b0 an by bn minus ln gamma a0. Achha, what kind of questions you might expect? You might expect, suppose if I am telling you that evidence lower bound, okay, so in evidence lower bound calculation, the expectations you are using, right? So expectations on the joint distribution, then expectation on the priors, okay, you are using. So this expectation uh, with reference to which variable you will be finding. So you can actually look at this particular ln p of beta given alpha. Okay, so expectation will be done in terms of beta alpha, whereas ln p of y given beta, the expectation with reference to beta only. Why? Because it is having only y. It is having only beta. Okay, so which is a random variable here? Y is your data. Okay, y is your data. So it does not have means with respect to y, you cannot, you don't have to do that. Okay, so in this way, so this kind of questions will be asked. Now next is E of with respect to beta ln q beta, ln q beta, okay, equals to half ln Sn m by 2, then 1 plus 2 pi ln 2 pi, 1 plus ln 2 pi. Okay, so where will you find this particular Sn? Go back to the earlier slide, find out the expression from that. Okay, so then E of alpha ln q alpha then this will be ln gamma function of an, okay, ln gamma function of an minus an minus 1 psi an minus ln of bn plus an. Achha, two more things actually I told. Achha, what did I write on this corner? I did write something in this corner. Was it the hierarchical model? No, achha, theek hai. Hierarchical model. So what are the use
Made a
of
graph. You had made a graph, sir.
graph? Yeah,
Elbow
achha,
versus
elbow.
iterations.
Yeah,
Elbow on the
iteration.
y-axis and iterations on
Ah,
the x-axis.
thank you, thank you, thank you.
That parabola.
It's not bad. Yeah, kind of. Yeah, kind of. Okay, so
Uh,
elbow should be working like this. It must not. It must be a
it must be
non-decreasing function.
non-decreasing, and the
Yeah.
number two is elbow can be optimized directly
Yeah, directly it can be
to
optimized.
find out the best parameters.
Yes, sure. So what are the use of or what elbow can do?
Yeah, uses of elbow.
Okay. Yeah.
Yes, sir.
So one is that elbow is non-decreasing. So if it is coming down, so there might be some problem in your code, or you have to initialize the parameters properly. Okay, because initialization is very difficult thing. Okay, and it is very tricky also. Okay, so if you suppose, why I'm telling it, that if you suppose um, the prior you are taking for beta, okay, the prior you are taking for beta, that is normal distribution I'm taking. Now normal distribution having two parameters, okay, one is mean, another is variance. So if you take wider variance, then it will be oscillating too much. Okay, it will be oscillating too much if you take higher spread or larger spread. Now, if you take too much smaller spread, then what will happen? Many of the values, they might be going outside the region. Okay, so what happens generally whenever you are going for this kind of Bayesian analysis? Okay, so don't rely on one method. Okay, you first do one thing. First, implement using give sampling if it is possible. Okay, and give sampling will, I told about these diagnostic tests. Okay, so in diagnostic tests, one very important component is your ESS. Okay, so where it is, I told about diagnostic test. Why did I tell it? Autocorrelation, cross correlation. Acha, I compared, here. So this ESS, so effective sample size. Now each iteration of or each sample drawing of give sampling is one variational inference iteration. So one iteration of variational inference is one sample of one sample of this particular give sampling or image sampling or any kind of. So now what happens that ESS effective sample size, it tells us that what should be the effective number of samples we should draw from the target distribution. Now depending upon different parameters, okay, some parameter might be telling that ESS is 700, some will be telling that no, it is 1200, somebody will tell that it is 20,000, okay, like this. So we have to set the boundary at the upper level. Okay, so ESS for all for running the whole program, okay, will be setting at the highest level, right? So we'll be setting as 20,000, though one parameter was telling that okay, it is having ESS as 700 only, right? So now those many iterations will be doing it for the variational inference. Okay, the example I have just given, so that is basically kind of a hypothetical example. This is how this Bayesian analysis is being done. And variation inference, it does not need any kind of diagnostic tests. Okay, autocorrelation we don't need, ESS we don't need, PSRF another diagnostic indicator. Okay, so it is also there, but it is also not needed. So it is also dependent upon some kind of autocorrelation, cross correlation thing actually. Okay, so this is how you have to do this Bayesian analysis, right? Now the thing is that now I am going into variational logistic regression. Okay, now so let me save it first, then I'll be going into next. Yeah. So after this variational logistic regression, I'll be going into this. Let's say here elbow is non-decreasing, and another is elbow can be optimized directly to get the best values of parameters. Okay, so this is what you can do with elbow. Achha, now we are coming to variational logistic regression. Now, as I was telling, that logistic regression is little bit tricky because the prior we use for the parameter is normal distribution, or from Gaussian family, or but the likelihood is Bernoulli likelihood, and it is having this sigmoid function in at its core. Okay, so this is the problem. So variational logistic regression. Okay, so here basically what is happening, I am writing directly the P of y. Okay, that is the response that will be given by P of y given w, or beta, P of y given beta multiplied by P of beta and d beta. Okay, so what we are doing here, I am trying to find out the marginal likelihood. Okay, so I am trying to find out the marginal likelihood. Okay, so this is coming as integration of product of I equals to 1 to n P of y I given beta. Okay, so this is a product. This is the likelihood basically. Then P of beta, then d beta. Okay, now P of y given beta, what I can write? So this is a sigmoid function. So sigmoid, what is sigmoid function? Sigmoid function, this is sigmoid. Okay, not the standard deviation. This is called a sigmoid function. Sigmoid function is 1 by 1 plus exponential of minus z. 1 by 1 plus exponential of minus z. Now this is having a very beautiful property. What is that property? That is, if you do derivative of this, okay, so del of sigma z with respect to z, if you do, then can anybody tell me what will be the derivative of this? What will be the derivative of this? Can anybody tell me? Quickly, but it's a very nice answer, a very and very exciting, interesting kind of answer. Can anybody tell me what will be the derivative of this? What is del sigma z, del sigma z given del z? It will be sigma z multiplied by 1 minus sigma z. This will be sigma z multiplied by 1 minus sigma z in sigma z. Okay, so you can actually do this. So let me just show it. Sigma del sigma z del z. So this is a by b. Okay, kind of function. So in denominator it will be square. Okay, and in numerator it will be first is the denominator as it is multiplied by so b del z of 1, so that will be 0, right? And minus it will be 1 minus, 1 plus exponential of minus z. So that will be exponential of minus z and negative will be coming. So this is exponential of minus z and this will be plus. So this is becoming exponential of minus z divided by 1 plus exponential of minus z into 1 by 1 plus exponential of minus z. Okay. So what is this one and what is this one? So this is actually sigmoid z. Okay. Now what is this one? This is 1 minus sigmoid z. So this is the beauty of sigmoid function. Is it okay? Do you understand this? This is the beauty of sigmoid z. Okay, sigmoid function, and that is why this is so much popular in case of deep learning. This is so much popular. Even uh, uh, tan hyperbolic function is also there. Tan inverse function. So the thing is sigmoid z. Okay, sigmoid is it is from 0 to 1. Okay, so open interval, not close interval, open interval. Okay, this is open interval. So sigmoid will be open interval 0 or 0 comma 1. And tan inverse, okay, these are all used as activation functions in deep learning. Okay, tan inverse, okay, so that is actually between minus 1, okay, open interval minus 1 and 1. Yeah, logarithmic tan, that is tan hyperbolic. Okay, so when you want output between minus 1 and 1, you go for tan inverse as the activation function. Otherwise, if you are interested in 0, 1, then you go for sigmoid function. Okay, so this is how basically it is done. So P of y given beta, so this is actually product of sigmoid z to the power yi, okay, multiplied by 1 minus sigmoid z to the power 1 minus yi. So this is also another very interesting kind of interpretation. Okay, so this is I equals to 1 to capital N. So this is becoming, this is, we can actually do it in a very nice way. That is coming as, it is coming as, why I'm writing z here? Z I'm writing because what is z here? Z is basically x beta. Okay, z is basically x beta. So I'm not writing x beta here because it will look clumsy. So that's why I'm using z. Okay, so this will become exponential z yi multiplied by sigmoid of minus z. Okay, so sigmoid z was 1 by 1 plus exponential of minus z. So sigmoid minus z is 1 by 1 plus exponential of z. Okay, so you can actually do this thing as homework. Okay, that how it is actually coming. Okay, and product of this. So this is the product. Okay, and we can write it as exponential z y, okay, sigmoid minus z. And what is z here? Z is x beta. That means predictor multiplied by the parameters of the model. Is it okay? Is it okay? Can I proceed? So you just do this as homework, that how it is actually coming. Okay, how it is actually coming. Okay, now the thing is that here the sigmoid function. Okay, so sigmoid function sigma z, okay, it is convex function. Okay, but problem is Murari bhaiya, Yes. So sigma z, it is a convex function, but the problem is that it is non-conjugate. Non-conjugate family. Okay. So this is the problem. Okay. So what we have to do, that we have to actually create a lower bound on this particular. Okay. We have to create a lower bound, which will be called as variational lower bound on this sigma z. Okay. So create a variational lower bound on sigma z. Okay. So this sigma z will be given as sigma. So it will be coming in terms of one free parameter. And this free parameter we have to actually tune. Okay. And based on that will be based on that. Thank you. Based on that, we can actually compute the logistic regression. Okay. So sigma of this xi, okay, exponential then z minus xi by 2. I'm writing the final result. This is actually coming from Taylor's uh, expansion. Okay, Taylor series expansion. From that actually it is coming. So lambda of xi multiplied by z square minus xi. Okay. So this is the lower bound. Okay, so this particular thing is the lower bound. So if we can maximize this lower bound, then we'll be reaching to the sigmoid function. Okay, so and where this lambda of xi, is 1 by 2 xi sigmoid function of xi minus half. Okay. Okay. So in this way, basically, we are creating a lower bound on the sigmoid function. Okay. And this lower bound will be used. Okay. This lower bound will be used for going for this particular logistic regression. Okay. So now, what will happen, that we can now tell the likelihood that P of y given beta, okay, P of y given beta is actually now can you understand why this particular thing had come? So this particular thing is now going to be used here. So P of y given beta is exponential of z y multiplied by sigmoid function of minus z, that is actually greater than equals to exponential of z y. Okay, so I'm just using this particular thing. I'm basically writing I'm using this particular expression in writing this particular expression. Okay, so exponential of zy, then sigmoid of xi exponential of minus a plus xi, okay, divided by 2 minus lambda xi, then z, it is not a, it is z. So z square minus xi square. Okay, so z square. Okay, so this is a lower bound. Now it has become. Okay, so this, why this is required? So this is now required that I can actually have a square term somewhere. Okay, square term somewhere, and because z is, what is z? Z is actually x beta. Okay, so z is x beta. So as this z is x beta, now my thing will be little bit easier. I can multiply. So this is the likelihood now, and I can now multiply normal distribution with this likelihood, and then I can actually take out this particular beta in a very nice way. Okay, so this is why this particular trick was used. That is called as local variational method. So did you understand this thing? So first is that I am writing, this is actually coming from Taylor's series expansion, Taylor's expansion. And it is actually telling you the local variational method. Okay, I'm basically looking at the local nature of this particular function. Okay, so now we are writing p of y w, that is the joint distribution, is equal to p of y given not w, beta. So beta multiplied by p of beta, it is actually greater than equals to a new function. I'm actually doing this likelihood. Now I'm having a new function with for that likelihood instead of the original likelihood. So h of beta comma xi multiplied by p of beta. Okay, now this h of beta comma xi, okay, will be equals to product of, sorry, product of I equals to 1 to capital N sigmoid function xi I, okay, then exponential of x transpose, sorry, beta transpose xi, beta transpose xi, then yi minus beta transpose xi plus xi divided by 2 minus lambda xi I, then beta transpose xi to the power 2 minus, so this would be inside one bracket, xi I square, sorry, xi I square here. Okay, so this is now my likelihood function. Okay, and this is a lower bound on the original sigmoid function. So now what will happen, that ln p of y given w multiplied by p of y given beta multiplied by p of beta, it is actually greater than equals to ln p of w plus summation of ln sigmoid xi I. So I am just using this particular expression here. Okay, xi I plus beta transpose xi yi minus beta transpose xi plus xi I by 2 minus lambda xi I, then beta transpose xi square minus xi I square. Okay, and then this one. Is it okay? And I equals to 1 to capital N. Now what will happen, that instead of PW, P beta, I'll be using this normal distribution. Okay, so normal distribution will be having the PDF as half, okay, then beta minus M naught transpose S naught inverse beta minus M naught. Okay, so this is basically the inside the exponential, whatever is there, it is actually coming out. Okay, so it's not p beta, it's ln p beta. Okay, so ln p y given beta multiplied by p of beta, okay, greater than equals to greater than equals to this plus this. Okay, so now if I do the little bit step jump, okay, so then basically if we have to add it here. Okay, so we have to put it here. So it will be put here, and then doing the computation, then you'll be finding that QW is coming as normal distributed. Sorry, Q beta is coming as normal distributed. Okay, with mean MN and variance covariance matrix as Sn. Okay, so what are the values there? So it will be Mn. So first Mn, yeah, Mn will be Sn inverse. Sorry, Sn. It's not an inverse. Sn then multiplied by S0 inverse. Okay, M0 plus summation of yi minus 1, yi minus half, okay, not 1, yi minus half into xi, I equals to 1 to capital M. Okay, and Sn equals to Sn inverse will be equals to S0 inverse plus 2 lambda of xi 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 transpose. Okay, so I equals to 1 to n. So this is what the posterior of the posterior parameters of the uh, model coefficient. Okay, now the thing is that here this xi I is actually a free parameter. Okay, so xi I is actually a free parameter. So first is you have to set this xi I somewhere. Okay, and try to find out for that value of xi I, you will be finding out that what is the value of mn and sn inverse or sn. Okay, and based on that you will be updating. So it is actually dependent upon xi I because it is a free parameter. Okay, so these free parameter basically what we'll be doing, that we have to identify that what is the best value of this particular free parameter. Okay, we have to identify. How to identify now? So we have to go for this marginal evidence or marginal likelihood. Okay, evidence, right? So ln of py equals to, we have already seen this, we actually started here, y given beta multiplied by p of beta, then d beta. Now that is actually greater than equals to ln integration of, so py instead of y beta, what we have done, we have actually used this h of beta comma xi multiplied by p of beta, then d beta. Okay, and this thing will be calling as uh, lower bound on this xi. Okay, now what will happen, that this xi will be updated iteration by iteration. Okay, xi will be updated iteration by iteration. So here something called as expectation maximization algorithm will be used, because this xi is a hidden parameter. Okay, xi is not coming in outside. Okay, it is nowhere important for us. But the thing is that to run this variational logistic regression, we have to find out what is the best value of this xi. Okay, so we'll be using something called as expectation maximization principle. Okay, there is a very close relationship between variational inference and expectation maximization. Okay, because both of them work on the principles of expectation. Okay, so here what we'll be doing, that we'll be finding out a function that will be called as q of xi new comma xi old. Okay, so in expectation max, where we do use this particular expectation maximization algorithm, there are wherever there we are having hidden variables. So hidden variables are basically eliminated. Okay, and to go for the inference, we actually find out we actually use this particular expectation maximization algorithm. Okay, now uh, this q of xi new comma xi old, this is basically a comparison between the uh, old value of xi and the new value of xi. It will be expectation of ln h beta xi p beta. Okay, that means I am basically finding out what is the expectation of the joint distribution. Okay, what is the expectation of the joint distribution? So now this I can write it as summation of ln sigmoid function of xi minus xi by 2, okay, minus lambda of xi, then xi transpose expected value of beta transpose, okay, then xi, this is basically one row of that X matrix, minus xi square, okay, plus some constant. Okay, so this is over I equals to 1 to capital N. Is it okay? So in this way, basically, I am finding out this particular Q function, which is the joint expected value of the joint distribution. Okay, and that expected value of the joint distribution, if I write it in the full form, then we'll be finding that this particular, it is actually going at the expectation of beta transpose there. Okay, now this particular function will be, you can say, using differentiation, will be finding out the derivative, and then we'll be doing this particular, we'll be equating it to 0. Okay, so by that, what will come? Okay, so derivative will be with respect to xi. Okay, so yeah, so now, yeah, anybody? Achha, theek hai. Okay, so now respect derivative we are finding out. So we are finding out this lambda xi I. Okay, then xi transpose e of beta transpose xi minus psi I square, and will be equating it to 0. Okay, so now psi I new, okay, that square will be coming as xi transpose e of beta transpose xi minus yeah, this one only, and then this is nothing but xi transpose e. What is e of expected value of beta transpose? That will be coming as sn plus mn transpose, okay, then xi, okay, and this is what will be the update in the xi value, okay, which is a free parameter, right? And based on this, what we are going to do, that will be actually doing the update. So how this model will work, that first you find out uh, for a for a particular value of xi, okay, for a particular value of xi, you find out that what will be the update. That will be update in the parameter of the beta, okay, that will be mn and sn inverse, okay. Now based on this, what will be the next value of xi, okay, what will be the next value of xi, ith xi, and based on that we'll be finding out, okay, and this is for each row of the observations, okay, this will be for each row of the observations. So this is a kind of that you are putting a parameter, okay, free parameter on this particular each row of the tabulated value of the y and x, okay, and you are trying to find out changing this particular xi I, how your values of this mn and sn is getting changed, okay. So this is what the variational logistic regression is, okay. Now we will be going into, this particular Python implementation of this variational, this univariate normal distribution, and then we'll be going into linear regression and logistic regression, okay. Okay, so yeah, so is it okay till now? I think lots of maths I have done, but the thing is that you have to digest it. Okay, and I am having high expectation on you people. I know surely you will be able to digest all these things, and you'll be coming out with some errors or some confusion, some doubts. Okay, so I make it as session 3 and 4, and let me save it as a PDF so that it will be easier for you to follow. Now I am going to uh, Python to implement those. Are you tired? So please respond. Are you people tired? I don't think so. You people are so energetic. Yes, sir. What? Yes, sir. No, no, you are not tired. Yeah, a little, but so you are a little tired, right? So I'm taking out. I'm being optimistic, and I'm telling that okay, we can work little more. So half an hour more. Okay. So let me show you the Python implementation of this particular. We'll be starting with the we'll be starting with the univariate Gaussian distribution. Yeah, I have written down almost everything. Okay, the formula especially, so that you can follow exactly what is happening. So can you see my screen? This the very first place I have written it wrong spelling. Yes, can you see this? ठीक है चलेगा. Okay, so this is that univariate Gaussian I was telling. So let us just run this first and check that what is it happening. So I'll be leaving you early by 6:15 around. Okay, I think within 15 minutes I can cover all this. Okay, and then this one. Acha, now what is the that whole formulation actually I have written here. Okay, so you can actually cross check. So data is xn. Here I am using n as the index. Okay, so capital N data points, IID random variable such that that xn is following normal distributed mu with mean mu and precision as tau. So mu tau given d data will be given as p of tau p of mu given t multiplied by p of d given mu comma t. Okay, so p of t tau is having a prior distribution as we are setting gamma distribution. Mu given t again normal distribution, and data given mu comma t tau, it is the data given mu comma tau inverse. Okay, and we have created this particular update in the distribution. Okay, so mu is coming as the distribution is coming as. So is it okay? Is it following the slide? Means whatever I discussed in the slide, is it following? Is it the same expression? Can you see? I am telling you repeatedly, if you are in this kind of Bayesian analysis, okay, if you are in Bayesian analysis, then you not even Bayesian analysis, even in probabilistic machine learning, deep learning, generative AI, and all these things, you must be very, you can say, observant. Okay, means whether these expressions are. Have you seen this expression somewhere else? So if you can remember that, then I think 70% job is over. Okay. So in many of the cases, you'll be finding that you have seen this kind of expression somewhere. So can you match that? Okay. So what distribution, probability distribution it is coming from? Okay, you can actually tell. So These are the expressions. Now I'm basically creating the data set. Okay, the data set is created. It is quite normal. It is not that very good. It's not a very good, you can say, normal distribution, because you can see the peak is not that good. Okay, so it is kind of flat and one side is little down. Now, if I plot that normal gamma, okay, so taking some samples, then how this normal gamma will be coming out? Okay, so normal gamma will be looking like this. So this is a contour plot. One side it is mu and another side it is tau. Okay, and the contour plot will look like this, normal gamma. Okay, this is just for example. Acha. So gamma distribution, it is coming as x to the power minus a minus 1, b to the power minus a, x to the power a minus 1, exponential of minus x by b. Okay, divided by gamma function of a. Now expected values, you can actually, expectation of tau, expectation of mu, you can write like this. Okay, now the q mu and the q tau you can write. Okay, so to create the PDF values, and then qx. Okay, so this is the function, these are the three functions I have written. So now you can take that posterior distribution is actually coming like this. Okay, posterior distribution is actually coming like this. So you have to now do little bit tweaking in the parameter generation, as well as setting up the parameters, as well as sample you are generating. Okay, how many samples you are generating? If you generate more and more samples, so samples are not having same connotation as the sampling methods. Okay, samples, I am telling that what are the values of this mu and tau you are generating over iterations. Okay, in this way. Is it okay? So I'll be sharing this with you. So please do some experimentation with this and try to create this kind of plot. Okay. So in that variational inference lecture, Professor Naik was telling about, might be, he was telling about that you have to basically create the distributional forms similar. Okay, it might be having parameter values different, but the distributional forms must be similar. And distributional forms, if it is similar, then this kind of contour plots will be coming as similar. Here also you can see that if I actually run it for more iterations, okay, then you can actually get quite similar kind of picture. Okay, yeah, you change the values, you just play with the code. Okay, but save it somewhere. Okay, I'll be sharing it in the canvas, but please, otherwise if you you must not mm, do some change, and then kind of it will be permanent and you will not be able to go back. Okay, so don't do like that. Achha, now regarding the linear regression using variational inference. Okay, so I am now creating a kind of mm, synthetic data set. Okay, and we are now trying to find out that exactly how does it work. Okay, so first is these are the necessary packages. Okay, second is I'm creating some synthetic data. I'm creating some synthetic data. Okay, and here you can see there are three predictors and one response variable. Okay, now now here are the hyperparameters I am selecting. Okay, here are the hyperparameters I am selecting. So this is the prior on the mean. Yeah. So a E value, C value, and D value. So the first one is basically the model. It is written like that. We are starting at W naught equals to, means the intercept as at 10 and W as 0, 0, 0. Okay, we are having three predictors. So the as three predictors are there, W is actually having three values. Okay, it requires. So next is that we are beginning the variational inference. So beta value and alpha value. Okay, so beta C prior is not defined. Beta C prior, what's up? Here we go to run. Yes, it is done. And here what is happening that uh, the predicted versus the actual, okay, we are actually getting this kind of plot. Okay, this is a predicted means the predicted y value. Okay, predicted y value and predict actual y value. Okay, we are comparing. And what is the RMSE? You can find the RMSE is coming as 2.91. Tomorrow we are going to see something very unique thing that as I was telling that suppose in this case what is happening that so let me just set the stage for tomorrow. Just 5 minutes I'll be talking on that after this running the code. Next is so this is the linear regression. For logistic regression, we can actually have this particular thing. A little bit complex. You have to understand it. Okay, and I think this is not a very difficult thing. Okay. This is why I always prefer this Jupyter notebook kind of notebooks so that I can actually write down the expressions and I can go on coding the things. Okay. So here then this one, then this one. Yeah. So these are two classes of data points. Then QW. QW means this is Q beta. Okay. Then this one. Okay. The contour plot. Then lower bound calculation. Then updating epsilon. Epsilon is the what is that xi there? That is epsilon here. It's C parameter. Yes. And then you have to see that whether the lower bound is getting stabilized after some time or not. Okay. So this is how variational logistic regression is being implemented. So you can just play with this, right? Take some data, real data if it is possible, classification data, or generate some real data, generate some synthetic data using this SciPy. So SciPy is having very nicely, it can generate some kind of data points, data sets, it can generate synthetic data. So you can actually use that to generate some data and you can test this kind of programs. Okay. So here another thing I wanted to share with you that local variational bound approximation. Okay, for non-conjugate case, it is basically written here. Okay, so should I share this particular thing with you or should I keep it aside? This is little bit that mathematics is required, that how that local variational upper bound is actually getting lower bound is getting calculated. So it is better to keep aside. Okay, I'm not going to do a share. Okay, very good. I wanted to see this interest. Okay, this interest, if I can ignite the interest in you, then my objective is accomplished. Okay. Okay, I'll share. No issues. Acha, before closing these sessions, let me just talk about little bit. Let me set the stage for tomorrow. Okay, just 5 minutes. Okay, not more than that. You just try to listen. So, what happens in see? Why are we talking about linear regression so much? Because linear regression is basically it is at the core of statistical as well as machine learning, statistical modeling as well as machine learning models. Okay, so let me just now what happens in case of linear regression. Okay, in case of linear regression, so basically what happens linear regression, the model is chosen as x beta plus suppose epsilon. Okay, so n cross 1, n cross p, p cross 1 and n cross 1. Okay, like this it is going. Now, how to find out this beta? There is a very quick method by which you can actually find out, that is known as normal equation. Okay, so what is normal equation? That tells me that beta is actually given by x transpose x inverse x transpose y, by this. Simple, you take the x matrix, take transpose, multiply it with x, okay, take inverse, then multiply it with x transpose, then multiply with y vector. So check that whether this order is correct or not. So beta is p cross 1, x transpose is p cross n, x is n cross p, okay, and inverse is p cross p, okay. Next is x transpose means p cross n, okay, and y is n cross 1. Okay, so p cross p multiplied by p cross n multiplied by n cross 1. So it is becoming p cross 1 finally. Okay, now the thing is, by this we can find out beta. Very good. But is it always applicable? It's not always applicable. So basically, now let me just give you the brief background where from this particular I think you might have heard of ridge regression, lasso, and all these things. So tomorrow, actually, we are going to cover those from Bayesian perspective. So we are going to cover those. Okay. So this beta, regarding this beta, uh, before that, let me just give little background on this. So you can understand this linear regression as a problem of solving systems of equation. System of equations. System of equations. Okay, so what is the system of equation? Suppose I am telling you y1 equals to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta p xp. Okay, see this is x1 1, x2 x1 comma 2. Okay, x1 comma p, x1 comma p. Okay, so this is the first row. This is the first row of data. Second one is y2 equals to beta naught plus beta 1 x 2 1 plus beta 2 x 2 2 plus dot 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 plus beta p x 2 p. Okay, like this going. Now yn is beta naught plus beta 1 x n1 plus beta 2 x n2 plus dot dot plus beta p x capital N p. So these are the equations basically, and we are trying to solve this. Okay, why are you solving this? Because we want to find out this beta naught, beta 1. These are the unknowns. Okay, beta naught, beta 1. All these are the unknowns we want to find out. Right now, there can be three cases possible. Okay, what are these three cases? One is that n is much larger than p. Okay. Second case is n equal to p. And third case is n less than p. So can anybody tell that what are these three situations? So if you have gone through matrices, okay, might be in UG, PG, you have gone through matrices, then there are equation solving. Okay, in that case, these are actually covered. So can anybody tell? So when number of rows is greater than p, when number of rows are less than p, and when number of rows is exactly equal to p. What are these system of equations? Can you find it out? So okay, this I'm giving homework for you. Okay, so tomorrow I'll be starting here. Okay, because tomorrow I'll be starting with sparsity. Okay, and in that sparsity, how basically we want to or how to work with in that case. Okay, I think enough for today. So please go through the slides and the video lecture. Okay, I think it will help you in understanding many things. Okay, so I'm stopping it. I'm stopping it. Okay. Okay, so Shinu, please close it. So any kind of doubt, any kind of questions you want to ask? If you want to ask any questions, please ask me. Thank you, thank you. I must thank you people that you are patiently listening me. Okay. So anything you want to tell? So when we are closing it, if you want to tell anything, everybody is telling thank you, sir. Are thank you means that you are trying to escape from me. Okay. So don't try to escape. 2 more days are there, and it will be little more mathematical tomorrow and day after tomorrow.